Today we're going to finish section 9.3, which is applications and probability. The first application that we had looked at and talked about last time was called odds. And then the second application that we were on last time when we left off was expected value. And so we're going to pick up on expected value with our final example. All right. And as I mentioned last time, it is a lottery example. So any given lottery, we know that the odds of winning the lottery are 55 million to 1. What is the probability of winning the lottery? So this first part of the question actually combines that idea of odds that we did last time with what we're going to do in the rest of the section about probability, or that's the rest of the problem about probability and expected value after that. So what would if the odds are 55 million to 1 to win, what is the probability of winning the lottery? Ooh, say that really loud, Alicia.
1 to 55 million and 1.
Okay, why is it 55 million and 1 and not 55 million?
Because it's the total, and so you have to combine.
Right. So does everybody remember that about odds? Odds and probability are not the same thing. There's definitely a relationship between them, but odds are the likelihood of losing versus the likelihood of winning kind of thing, whereas probability is the likelihood of winning compared to all possible outcomes. So here that would be 55 million, 1. So let's take a look then at what happens in this particular scenario. If the grand prize is $14 million and a ticket costs $5, is the game fair? And we talked about the idea of being fair last time as well. Do you remember what we said it meant for an experiment to be fair? Yeah, expected value is 0. So anytime we're mathematically talking about this idea of being fair, we're talking about an expected value being 0. And I mentioned last time that not all the problems are always just win or loss. You might have different ways of winning, right? What if there's one person who wins $14 million and there's 3 other people who win, like $10 million? Well, that means we've got more than one possible outcome. But in this scenario, there's not. There's 2 possible outcomes. What are they? You win, how much? 14 million, or you lose your $5, right? I mean, that's the options. Make sense? Okay, so we actually would have the probability of winning times the value of winning and then added to that, we would have the probability of losing and the value of losing. Let's do the losing part first. Let's just do the value part first of losing. What is the value if you lose? -5. Okay, remember, value has to do with how your money in your wallet changes kind of thing. -5, that is the value of if you lose. What is the probability then of losing? Okay, it's related to that, but what did you say, Alicia?
55 million over 55 million.
Right, so the one that's on part A is actually the probability of winning. We can write that in if you'd like. This is the 1 over the 55 million and 1. So if the probability of winning is 1 to 55 million and 1, then the probability of losing is 50 million to 50 million 1. Okay, does that make sense for everybody?
Is it 50 or 55?
Oh, did I change my numbers in there? It's 55, thank you. 55s. Okay, the rest of it's 55, so I got this part right, good. Okay then, the last thing to fill in before we actually do our calculation is what is the value of winning? Okay, so you do win 14 million, but it cost you $5 to play, right? So you've somehow got to make amends for that $5. So what would you have to do? Yeah, you'd have to subtract, right? So you'd have your 14 million minus 5. So that would be what? 13 million. 999,000. What else? 995, right, yeah. Let me shift this over just a little bit. Okay, does that make sense to everybody?
Yeah.
Every time you win, you've still had to pay to play. So you've always got to take off the cost to play versus what you've won in the game. All right, if you will grab your calculators, multiply this out. Keep in mind that what you're looking for, what type of an answer you should get is a dollar amount answer, right? Dollars and cents, like this is money. So whatever answer we get, we need to round to the nearest dollar, right? Or cents, actually, would be even appropriate. We could do cents. So we'll say 2 decimal places, all right? So nothing more than that. I'm going to go ahead and put my dollar sign. When you get a value, tell me what you get. Is it 0? No, it's not 0. What is it? Throw me out something.
5, 4, 5.
What's that?
0.7545.
That's not what I have written down. What do you have, Alicia?
I have -4.75.
Okay, that's what I have as well. See if you can take a look back at what you entered. There may be a typo in what you've got in there, Emily. -4.75. Did anybody else have the -4.75? Okay, I got a couple of notes. Okay, it is -4.75. Obviously, the right answer matters. For the purposes of the question that's actually being asked, is it fair or not? Both of those answers, whether you'd actually gotten the 0.75 or a -4.75, would be the answer of no, it's not fair. Why? No, yeah, because it's not 0. The expected value E is not equal to 0. That's what makes it not fair. What does it really mean, though? We talked about this last time. So we paid $5 to play, and we would expect that over time, every time I paid $5 to pay, on average, I lose $4.75, right? I mean, like that's what's going on. The playing actually costs me $4.75 every time, even though I'm paying $5. So it's not technically how it works. It's an average, right? Yeah. So take a look at what happens next in this particular situation. As with many state lotteries, the proceeds are often said to benefit education. Under these conditions, if all proceeds benefited education and 1 million tickets are sold, what is the expected value from the lottery sales? So we've got 1 million tickets, and it costs $5 to play, right? So one might think that it's simply 5 million. Are you with me? $5 per ticket, there's 1 million tickets, okay? It's not quite what the question's asking. That assumes that nobody wins, right? If that's the case, 5 times your 1 million tickets. So what it's actually referencing is going back and taking a look at the expected value, the over time stuff. Expected over time, it costs each one of you who plays, in this scenario, $4.75. But if it costs you $4.75, then it makes whoever's running the lottery $4.75. Make sense? Like their profit on average would be $4.75. Your loss on average is $4.75. So this expected value that was negative over here is a negative to the customer, the person who's playing the game. But that would be a positive to the person running the game, okay, whoever that is. So on this problem, we're actually saying that on average, the state, in this case, would make $4.75, and they would be selling 1 million lottery tickets. And so, if we multiply this, what do we get? $4,750,000. So that's kind of cool, right? $4 million went to education in this scenario, on average. The problem is that averages don't really work, right? I mean, everybody who wins the lottery is super excited, even though on average they never should have won, right? Like, statistically speaking, nobody wins the lottery. But somebody usually does, eventually, right? Like, it does happen. That's why they play, right? Like, somebody's got to win is the theory. And eventually, over time, somebody usually does win. But that doesn't mean that, so there's these extremes, right? Most people are going to lose. Somebody's going to win, and there's an average of what's happening overall. But let's actually look at the real-life scenario of the actual outcomes that are possible in this scenario. So this is the average case, C, right? That's on average what happens, on average. But there's really only two possibilities here. If this is a lottery where somebody's playing and it's just a one-time thing, right, this time around or whatever, there's two possibilities, is that no one wins. And typically speaking, in state lotteries, when no one wins, the jackpot goes up and they run the lottery again. Y'all know what I'm talking about, right? You've seen enough of the signs and stuff in the state to know that's how it works. Okay, but in a one-time scenario, we're looking at one case of this happening. No one wins. And then, of course, the secondary case is that someone does win. And for the purposes of what we're doing, we're just talking about one person winning. And I also realize that that doesn't always play out for the scenario and in the way lotteries always work, but for the purposes of what we're doing. So if no one wins, what really happened is that each person paid $5 to play and there were 1 million tickets sold, right? That's what I was talking about earlier. This is the no one wins scenario, and then we actually have $5 million. Okay, agreed? Yeah. What happens if somebody does win? How much do people pay to play? $5 a piece, 1 million tickets, so $5 million, right? $5 million was brought in from the sale of the tickets. But now somebody wins. How much do they win? They win $14 million. So what's the outcome when someone actually wins? Y'all know what the answer is. Somebody tell me so we can keep going. It's -9, right? -9 million. We're just subtracting those values and we end up with a negative. That's the real outcome. The real outcome is that you either make 5 million or you'll lose 9 million in the budget, so to speak, right? It's a really tricky thing because people want to be like, they like to promote education as being the reason why we want to do that. I don't know why education is like, maybe it's just because it pulls at everybody's heartstrings a little bit. Like, oh, yeah, I want to help education. Let's do it that way. And so they tend to want to use education as the crux for making certain things possible. When we lived in Ohio, they were wanting to, in Ohio, they don't have a lot of Indian ground land like we do here, right, where you can put casinos on. So they were wanting to make casinos legal, and so they kept using education as the reason for wanting to make the casinos. A certain percentage of the casinos' earnings were going to go back to education. So education is used as a toy in these games a lot of the time, actually. But the reality is that if you really think like lottery, fantastic, great education, what you're saying is, I want all these people who've paid $5 to lose their money, right? That's what you're really saying. Because if you really want someone to win, it's not going to help education because somebody's going to take all the money instead. Those are the two outcomes. So it's kind of an interesting scenario.